people on Zoom. Just do a quick.
Hi, everyone.
Thank you for coming to this session for the New Technologies in Mathematics seminar. Today, we're very happy to have Conal and Aryo, who are currently working at EPFL, and they will tell us how far a transformer can reason. Conal and Aryo, take it away.
Thanks. Thank you for having us, and thanks for joining this talk. So I'm just gonna share the screen. So again, everything's good?
Yes.
Sorry. So yeah, our talk is about how far can transformers reason, the Globality barrier, and Inductive Scratchpad. And first, I'm going to talk through the first part, and then Colin is going to go deeper into the theoretical part. And this is a joint work with Emmanuel Abbé, Sami Bendiu, and Omid Saremi. So first of all, what is reasoning? So I think it's not a super well-defined concept, but first of all, it's similar to generalization in machine learning in general, but we have some maybe criteria for it. So we want it to be rather efficient, and we want it to have some compositional nature to it. So for example, it's kind of different from the nearest neighbor type of generalization that we have seen so many examples that and our kind of input space is so low dimensional that we can simply just check the nearest neighbor and give some answer based on that. So for example, and also some other important factors that we usually check for reasoning is like factors like out of distribution generalization and also length generalization. So for example, in this example, we have a task that given two symbols, we want to tell whether they are different or the same. And we have some symbols on the left, which is the training set. And during tests, we can see new samples, which would be just normal generalization, but we can also have samples that we can have unseen samples, symbols that would be this out of distribution generalization, or we can have a new kind of longer sequences. So this kind of out of distribution generalization kind of make that sort of a nearest neighbor and memorization approach impossible. And reasoning is kind of relevant everywhere, but maybe more pronounced in logic, mathematics, algorithms, and planning, because usually tasks are not do not lie in a low-dimensional manifold. For example, you can take arithmetic. You have a number of digits, and you can just change any of them. So we have an exponentially large input space. And the other thing is that changing just maybe a token in the input would change the output significantly. So for example, if you're computing the parity and you just change one of the input bits, it would completely change the output. And usually multiple steps and search are required in reasoning tasks. So to answer whether transformers can reason or not, there has been some success stories. So for example, we have alpha geometry and alpha proof that can solve mathematical Olympiad questions quite well. Or for example, font search. But still, we see that for some simple problems like arithmetic, just summing numbers or multiplying them and so on, transformers fail quite early, like even for 6, 7 digits for multiplication. And also they often struggle with length generalization. Another thing that at least current approaches have is that they often rely on external components to maybe compensate for these issues. So for example, they rely on Python code and interpreter or calculator or similar stuff. So we also did some simple experiments with ChatGPT. So we gave it 5 people, and between these 5 people, there is 4 relations, so that you can infer basically we say that, for example, Marco is taller than Patricia, Bob is taller than Marco, and so on. And we have 4 relations, so you can have the complete infer the complete order. And we ask the relation between two people that is just given by composing 2 of these input relations. And we tested this on 1,000 samples on ChatGPT 3.5. And actually, it just failed for 40% of them. So this system code has kind of 60% accuracy, even for this simple sample, simple example that requires just combining two clauses. And we tried also a more mathematical version. So for example, we gave it four equivalences and asked whether it can combine two of them to get the answer or not. And this one was also kind of interesting because first it tried to do the math and it failed. And next we asked it to just consider the equivalences and see whether you can combine them such that you get this final equivalence, and it failed again. So it seems that at least this was at least with ChatGPT 3.5. ChatGPT 4 already does a bit better, but still they struggle with this basic sort of reasoning. So we kind of focus on this sort of deductive reasoning. So we have relations like A gives B and B gives C, and we want to conclude that A gives C. And this is, I think, very important in general reasoning and in particular mathematical reasoning because it appears basically everywhere in our reasoning process. And it is also important in planning because this instead of these relations, we can have priorities or other sort of comparisons that isn't necessary for planning. And we can always model such problems with basically some nodes and some edges between these nodes. So for example, we have here an edge from A to D and then from D to F. Or and for example, we ask whether there is a path between A to F or A to C. So this is the kind of abstract version of this reasoning problem. And here we kind of focus on this easier format of input and this abstract version, which we only have symbols. But in real world, we have clauses instead of these symbols, and it would just make everything even more complicated. So this is how we define our task. So we represent input as basically the edge list of the graph. So for example, this input basically says that J goes to B, A goes to X, C goes to M, N to J, and X to C. And we ask whether A and M are connected or not, or basically whether there is a directed path between A to N. And we will shortly see what makes this task hard, but as you can expect, if we have a larger graph, if the distance is higher or if the diameter of the graph is higher, all of these factors kind of contribute to the hardness. So first we had a very simple experiment. So we just generated some graphs using basically Aryo graphs with 24 nodes and 24 edges. And we trained the GPT-2 style architecture on this task. And we observed that it actually can reach an accuracy of 80%. And after that point, it cannot go beyond that, kind of, it plateaus at that point. But at least this 80% is much better than trivial 50%. So we had a question that whether the model is doing the right thing, or is it just relying on some sort of correlations and just some shortcuts that are not the correct reasoning, but they're just present in our distribution. So to kind of answer this question, we tried an OOD dataset. So we kept the number of nodes and edges the same. So we have, again, 24 edges and 24 nodes. But this time we just used a different generation process. So this time the graphs are not coming from Aryo Lotfi distribution, but they are rather just basically each graph is a collection of cycles. And for this distribution, for this new distribution, we can check that basically the accuracy of the model becomes 50%. Which is quite interesting because we didn't even change the number of nodes and edges. So the length of the input is the same. So there is no kind of length generalization. It's just another kind of input distribution. And we kind of investigated this a bit further and realized that basically what the model was doing in the Aryo case was that it was checking the source nodes out degree and the target destination node's input degree. And it was just using some linear classification on these two parameters, basically just checking that if the source out degree is larger than 1, and if the sink's in degree is larger than 1, and the end of these two statements. It was highly correlated with this predictor. So it was basically just relying on some correlation, which was working for that specific distribution, but not in general. So to kind of have a distribution that really measures if the transformer is doing the correct reasoning or not, we created a new dataset, which is our main dataset for the rest of this talk. So we have for number n, we have 2n nodes and 2n edges between them. And these 2n nodes and edges either form 2 cycles of size n or one cycle of size 2n. And if you have 2 cycles of size n, as you can see on the left, we query for 2 nodes in 2 different cycles that are not connected. So for example, we ask about a and m in the left example, and the label is 0 because they're not connected. And when we have one big cycle of size 2n, we query for 2 nodes which are at distance n from each other. So in this example again, a and m. And the label in this case is of course 1. And again, the format of input is just the edge list, where each vertex is represented by a token in the transformer, and the output is just a 0 or 1 label. The thing about this dataset is that first of all, the input degree and the in degree and out degree of every node is the same, both for the positive samples and for the negative samples. But actually, you can go even a step further, and you can see that every neighborhood of each of these nodes is kind of the same in the two examples. So maybe it's a bit hard to see it for n equals 3, but if you consider just a large n, if you check the neighborhood of 2 nodes, for example, a neighborhood of constant size 5 or something, you can see that the neighborhood of the nodes in the positive samples and the negative samples is the same. So that is kind of what makes this data set hard, as we will see. Just checking time. So we checked this new dataset and we trained the GPT-2 decoder-only transformers on this task. This is pre-training, so we're not using a pre-trained model. And we tried different model sizes, and for all of them, it seems that the number of iterations that we need, so also we are using fresh samples, so it kind of is the number of samples that we are using also. It kind of it grows exponentially as we increase the size of the problem. Basically, even with a small model, when we have size 7, we cannot learn this problem without going above 100k iterations. And again, to explain, just to give you a hint that why this task is hard, the reason is that as we increase n, to answer the question, to give some partial information, about, to have just some clue about the output, to say whether it's 0 or 1, we have to at least look at n-1 edges. Because if we, n edges, because if we look at any n-1 edges, and this means at least n-1 tokens, we cannot get any information on the label. Is there any questions so far, by the way? Or should I
What's the
continue?
depth of the transformer?
Sorry?
What's the depth of the transformer?
So I think we've varied it for 10, 25, and 85. But I think for the 10 million model, probably around it was 8. And so I think probably some numbers like 8, 12, and 16, I guess,
Okay.
in that range. Yeah. Yeah, so now to formalize this thing that we need at least n-1 tokens to get something on the input. We define globality degree as a measure of difficulty, which is the number of tokens needed along with the histogram of the tokens, which we will explain just in a few seconds. to achieve a non-trivial correlation with the output label. So to put it more precisely, we are looking for the minimum number of tokens, such that if we look at those tokens and the input histogram in general, we can get a mutual information, an inverse polynomial mutual information with the output. And by this input histogram, we mean simply just how many times each token is appearing in the sequence in total. So it's just like a bag of words information without any information about the position of the tokens. And basically, we also, when we say n or inverse polynomial, this is in n, which is the number of input tokens that the transformer receives. And so related to this measure, for example, just to give you a few examples, if you have a parity of a sparse parity function of degree k in a dimension of n, then the parity has globality of a minimum of k and n minus k, because we need to at least have a. First, I'm going to explain the k, because things that you need to look at and attend to these k bits to get just the answer with compute parity. And if you have k minus 1 bits, you cannot say anything about the parity result. So you get zero mutual information. And the reason that we have k, a minimum of k and n minus k, is that you have the histogram. So basically based on the histogram, you know that how many you kind of know that what's the, for example, the sum of the bits. So if, for example, k is very large, you can just check the remaining n minus k bits to get the parity of these k bits. And for the cycle task, the globality is larger than n minus 1, because any n minus 1 edges and any n minus 1 tokens not tell us anything about the final label. And we believe this measure is a bit more intuitive and more relevant to transformers than previous measures like statistical query dimension, cross predictability, noise sensitivity, and initial alignment. Colin will go deeper into the theoretical side at the second half of the talk. And we have a conjecture which says that a task is a task given by some distribution is weakly learnable by a regular transformer if and only if its globality is constant. And first of all, by efficiently, we mean polytime in the number of tokens n. And by weakly, we mean at least some accuracy, which is inverse polynomial, again in n. By regular transformer, we mean a transformer that is polysize, again in n, the number of tokens, uses bidirectional attention, and also has learnable absolute positional embedding initialized randomly. And of course, this conjecture has some conditions. So for example, we assume some conditions on the distribution of the data. So for example, there is no sample that is that appears so frequently that just memorizing that would give you this accuracy. And also for the positive part of this conjecture, we have it only for the, I mean, this is a conjecture, but we only conjecture it for the case that alphabet is constant. So this is the conjecture, and so far it's also supported by experiments. I mean, just as you saw, kind of when we increase this, the complexity of the task and the number of tokens, which was a scaling with n linearly, we could see that the learning complexity of the task, the time complexity was exponential in n, which is supporting this conjecture. So now we are going to kind of answer what we can do to kind of learn these hard tasks which have high globality and require some sort of global reasoning. And the answer is to use a scratchpad, or maybe more commonly known as a chain of thought. So basically, the thing is that we have some inputs like x1 to xn, and we want to learn one final label like y, which we call it here ym. And the thing is that computing y from x1 to xn may require some large kind of a very global kind of reasoning, and it would be a high globality function. But what we can do is to define basically intermediate targets, such as y1 to ym minus 1 here, such that they kind of guide us through the final answer. And each of these intermediate targets are kind of easy based on the previous ones. Basically taking just small steps. So to make it a bit more formal, when we have this x1 to xm and we want to xn and we want to predict y1 to ym autoregressively. So we first predict y1 and then y2 and so on until yn. We can define the autoregressive version of the globality in a very similar way. So it's again the minimum of number of tokens such that any of these intermediate targets, so any of these yi's, can be computed based on at most, sorry, not can be computed, but can be at least to be able to just get some minimal information on it based on x1 to xn and y1 to yi minus 1. So it's basically just saying that each of these targets, y1 to ym, to have a globality of at most k based on all of the previous tokens, which is the input and the intermediate scratchpad or chain of flow tokens that are generated so far. And based on the conjecture to have efficient learning, which is the polytime learning, we want each of these yi's, each of these intermediate targets to be a constant globality function based on the previous input tokens. So for example, take the parity example again. We all know that learning parities is quite hard and challenging, especially if as the degree of the parity grows. But one common version of the scratchpad idea that is often used for parities is that to just record the cumulative parities. So for example, when we have x1 to xn as the input, we compute first x1, then x1, x2, then x1, x2, x3, and so on until we compute x1 to xk. And basically, as you can see in this setting, the globality in this setting is basically 2. Because each of these intermediate targets, each of these cumulative parities, can be computed basically only based on 2 tokens, which is the previous intermediate cumulative parity and 1 input bit. And just to clarify, the scratchpad or chain of our scratchpad setting, which is quite common, is that during training, we train it with the x1 to xn and also y1 to ym, all of that given to the model. But during inference, we only give the input x1 to xn to the model, and the model has to predict y1 to ym, all of it together in an autoregressive fashion. So basically, for example, this scratchpad idea for parity can break that globality of k, minimum of k and n minus k into just 2, which makes this task efficiently learnable. And we can do basically the same for our cycles task. So for example, for the cycles task, the most natural idea to try is to just do some search. So for example, we start from the source node and we do a DFS or BFS, which is the same in this example. Search from that node and we start to list the nodes that we can reach. And if we reach the target node, we know that the label is 1. And if we get back to the start node, we know that we have 2 cycles and we haven't seen the target, so the label is 0. So you can see the examples in this slide. So this again, to support our claims, we can see that when we do this scratchpad idea, we can basically break that globality barrier that we had. And as you can see, we can just learn the task quite easily as the size of the problem and its complexity grows, comparing to the no scratchpad version. So just to wrap up at this point, first, the one important point is that using the scratchpad is changing the game because we are training with more information, and this is basically using more data and is kind of changing the game. So there is no miracle with this scratchpad idea. And as Colin will go deeper into this part, we conjecture that unsupervised forms of a scratchpad, which is just searching for a good scratchpad or ideas like that, cannot break the globality barrier. So there is kind of no free lunch. And another problem that we'll shortly see is that even when we use the scratchpads, they are not necessarily robust to, for example, OD samples or samples that require more reasoning. So in particular, we have one example. So we take this cycles task with 24 nodes and 24 edges, but with one difference. With the difference that during training, we have two sort of samples. So first are the samples of cycle sizes 6 and 18. And in this case, the cycles are the nodes are not connected. And the query node is always in this cycle of size 6. So it kind of has, it's in the smaller cycle. And for the positive samples, we have, again, a cycle of size 24. But this time, and of course, the nodes are connected. But this time, the distance between the query nodes is just 6. So basically, during training, whether the answer is positive or negative, we only need 6 reasoning steps. However, at test, we used our normal cycles task distribution, which is cycle sizes of 12 of 12 when they're not connected, and distance of 12 when they are. So basically, at test, we need 12 reasoning steps. And as you can see in this plot, when we train on this distribution and we just test on the harder, kind of more complex distribution, we can't get any generalization. And again, just note that the size of the problem in the number of tokens sense is the same. So there is no length generalization on the number of tokens that the transformer has to handle. But the only kind of length OOD generalization is on the number of reasoning steps required. And to kind of solve this issue, we can notice that there is a repetitive pattern in our scratchpad. So you can see that given, for example, we have the question here, and we have the scratchpad A goes to X, X to C, and C to M, and finally the label is 1. But you can see that basically the way that we compute X from A, which is just looking up the neighbor of A in the graph, is basically the same way that we compute C from X, which is again looking the neighbor of X in the graph, and so on to get M from C. So basically, we have some sort of function which is just giving the next neighbor, which we apply to question and A to get X, and we apply to question and X to get C, and so on. And this repetitive structure is something that we can benefit from. So to make it a bit more formal, we have the input question, and we assume that we have some states, which each state is given by the previous state and the question. So the first state, the 0 kind of state, is given by the question only, and after that, each state is just given by question and the previous one. And of course, at some point, we will generate the end of sequence token and the process will end. So we define a new sort of a scratchpad, which is called inductive scratchpad, to kind of handle this sort of tasks. So it uses the same scratchpad format as we had. So the previous scratchpad format that we were using was just question, state 0, state 1, state 2, so on until state k, which is also giving the answer. We just make 2 modifications. We introduce 2 new tokens. First, we have the start token, which we put just after the question. And then we have the state token, which we put after each state. So the new, you can see the new, so I think you cannot see my pointer, but you can see the new scratchpad format in the middle of the slide. And basically, based on these 2 special tokens, we can mask the attentions and also reindex position of the tokens, such that we get the inductive behavior or Markovian behavior. And by this Markovian behavior or inductive behavior, we mean that basically in this box in the lower part of the slide, we mean that the fact that model should give you based on the question and state 0 to state I, it should give you the state I plus 1 becomes equivalent using this masking and pre-indexing of the positions of the tokens becomes equivalent to getting a state I plus 1 just from the question and state I. So this is just something that we can handle easily by masking the tokens dynamically based on these two special tokens. So basically we get this equivalence both at the training time and at inference. And so Inductive Scratchpad has better better OD generalization. So for example, we tried the Inductive Scratchpad for the problem that we saw just a few minutes ago with the cycles task. And as you can see, the format of the normal Scratchpad and the Inductive Scratchpad for this task are not that different. So they're quite similar. It's just the introduction of these new tokens. And you can see, but just with this small modification and the modification in the architecture, we can get perfect OOD generalization. And the reason for this is that Inductive Scratchpad just learns the induction step, or basically the state transition function, and really doesn't care about the number of reasoning steps. While the normal Scratchpad usually overfits to kind of the whole sequence, and it doesn't really use that kind of inductive or repetitive behavior that maybe is present in the Scratchpad. We also present this idea for two other tasks. So we can have it for, I'm gonna go quickly over these parts, but we tested for the parity, and we use quite a simple format for parity. So for example, as you can see, we have an example, for example, for 6 bits, 0, 1, 1, 0, 0, 1. And what we do is that we define each state to be a pointer to the current bit, the value of the current bit, and the cumulative parity up to this bit. So you can see how the Scratchpad looks at the bottom of the slide. So each state is colored in a different color. So again, the pointer, the value of the bit indicated by the pointer, and the current value of the cumulative parity. And we use this format of the Scratchpad, and we get very good results. So, for example, we train on parities of up to length 30, and we test on parities up to length 60. And as you can see, we can almost go perfectly up to size parities of size 55, which is almost double length generalization. And it's also a very small model of 10 million parameters. And we checked the same thing for the addition task, which is again another task which is known to be hard in length generalization setting. And we see that if we do this kind of the same idea, so we have basically a pointer to the least significant digit of the first number, a pointer to the least significant digit to the second number, and then the value of them, and just adding them and going on. So this is each of the states. We can, sorry, I'm gonna skip this. We can easily see that for the orange curve, basically, that we again can train on size additions of size 10, and we can get almost 60% accuracy up to size, for example, 20, or almost perfect accuracy up to size 18, which is again almost double length generalization. And we also introduce one more format for the addition task. Sorry, we also introduce one other format for the addition task, which is a bit more heavier on the input representation. But again, you can see how it looks on at the bottom of the slide. Again, we have the different states, and at each state we just add again the least significant digits of the numbers and go to the next digit. And we also keep the carry and keep track of carry and so on. You can see the more details in the paper. And even this method is a bit heavier on the input formatting, but this method can generalize to size 26 when trained on size 4, which is more than 6 times length generalization. So to wrap up the inductive Scratchpad part, this is something that can give us better OOD generalization when more reasoning steps is needed, because it just learns the kind of reasoning step instead of all the reasoning kind of path. So it just learns how to go to the next part of the reasoning state kind of. And it's also very easily integrable into common language models, because we just introduce 2 new tokens and we do attention masking based on those new tokens. And this is also very suitable for low resource environments, because it basically reduces the effective context size, because it ignores the previous states other than the penultimate one, which is kind of basically reducing the context length of the transformer. And it has some connections, of course, to universal transformers, which are a form of recurrent transformers, and relative positional embeddings, as used in other papers.
I missed a point of definition when you say that this model ignores the previous state. Is that just because the training data encourages it to learn to that, or is there some other change in the model that makes it ignore that?
So in the inductive Scratchpad idea, right?
Yeah.
Oh yeah, so basically we just make a modification in the Scratchpad itself. It looks very similar to the normal Scratchpad, the inductive and normal Scratchpad. So basically it's just these new tokens, the start token and this hash token, which we use for end of each state. So yeah, sorry if I wasn't clear before. So we have this start token, which we put at the beginning, and we have this hash token, which is the state token, which we put after each state. And in the architecture itself, we mask the attentions, the attention matrices, and also we also reindex the position of the tokens.
Okay, so the model changes what it.
Yeah, exactly. The model changes.
I just at this initial stage of the attention.
Exactly. Yeah.
Okay,
So we
okay.
change the attention and position of the.
Okay, got it. Yeah.
Yeah. Oh yeah. Also, just to make it clear, it only changes the transformer behavior for these 2 special tokens. So that's the reason that I would say it's easily integrable into common language models, because for the normal input, which doesn't use these 2 special tokens, we would get the normal behavior of the transformer.
Thanks.
So yeah, now we go to the Collins part.
So now let's go back to the globality degree. As mentioned, it's the minimum size of a set of input tokens that, together with histogram, allows you to determine the function with non-trivial accuracy. The reason why we think that's relevant is because it's an estimate of the degree to which this function will tend to correlate with a random function. Or when we say random function, we mean not actually the thing we get with the random lookup table, but the type of function we tend to get if we start haphazardly combining things. In particular, it's the kind of function we get if we make a transformer or neural net and just set the weights randomly without knowing what the target function is. So to the degree that the globality is constant, we would expect a correlation in this inverse polynomial between the target function and a typical random function of this sort. Otherwise, we'd expect a correlation which is smaller than anything this inverse polynomial. And as mentioned, we've conjectured that a task is efficiently weakly learnable, well, if and only if it has constant globality under some assumptions. The reason this holds in more detail is that in order to train a transformer, we're typically going to use some form of gradient descent, i.e., at any given time, we look at our existing model and then try to check for each weight if increasing or decreasing that weight makes the model more accurate. So if we can find a way to perturb the weights that makes the model more accurate, then it will gradually improve. If we can't find such perturbation, the model is more or less stuck, and we'd expect not to make progress. So in order to get anywhere, we typically expect that we'd need at least one of the derivatives of the function's behavior with respect to its edge weights to be correlated with the function we're trying to learn. And you'd expect each of these derivatives to be essentially random. So since a high globality function is essentially uncorrelated with a random function, and we'd expect that we won't make progress. Okay, now the hard part of actually proving that is that the derivatives of the transform with respect to its weights are not really necessarily random functions in the sense I mean. We can reasonably argue by symmetry that at initialization they'll be random in the relevant sense, but that could change. Our best plan for dealing with this is to argue that as long as the functions are sufficiently random, a weights will evolve in essentially the same way when trained on their actual function as they would evolve if trained on a function where we just gave everything a random output. So to the degree that the net's behavior will remain sufficiently random when trained on that function, and we can then argue that if the derivatives will remain sufficiently disorganized that we'll fail to learn. Among other things, if we have an input distribution where the input tokens are all identically distributed, we can use symmetry under rearrangement of inputs and argue that all the weights probability distributions will stay symmetric under rearrangements of inputs, which allows us to proceed and make this proof. However, that's a fairly specific assumption. So one of the few cases which we can actually prove which doesn't have this property is a variant of the cycle task, in which there's either one cycle of length 3n or 3 cycles of length n. In this task, we either pick 3 anchor points which are equidistant around the large cycle, or one anchor on each of the cycles when there are 3 of them, and call those A0, B0, and C0. Then we number every other vertex x based off its distance from the closest anchor vertex x, and then assign each of the 3 vertices at a given distance labels A, B, and C randomly. Then we provide the net the details on what vertex each other vertex's edge goes to, and ask it to figure out if there are 3 cycles or 1. In this case, we actually can prove that a regular transformer trained with gradient descent cannot learn this task in polynomial time. Now, the key part of actually being able to prove that is to observe that it's the part of the input distribution explaining how the vertices AI, BI, and CI connect to AI plus 1, BI plus 1, and CI plus 1 is essentially a permutation on 3 elements. And the overall behavior of the graph is essentially equivalent to taking the product of all these permutations and asking whether it's the identity or a cyclic permutation. So it suffices to prove that this transformer can't learn that task, essentially. In particular, we allow for any given I and j, there exists a permutation of input bits, which essentially switches the permutation corresponding to how the I vertices link to the I plus 1 vertices, and the permutation listing how the j vertices link to the j plus 1 vertices. So that gives us a permutation of the inputs such that the net's behavior will be symmetric under the null distribution, which then allows us to prove that if the derivatives retain the necessary properties to prove that if the gradient differences are essentially 0 and the net doesn't learn anything different under the actual function than if the outputs were random. As such, the transformer can't learn this. We previously noted that for some problems with high globality, we can get around the problem by using a scratchpad. However, in most of these problems, we assumed that when training the net, we know what the correct thing to write in the scratchpad is, which isn't necessarily realistic. If we know how to compute the appropriate elements of the scratchpad from the inputs, but we could just skip to giving the net the scratchpad to begin with rather than trying to train it to do that. And you can have a case where there's some small number of samples where we know what the correct scratchpad could look like, but don't know it for everything. But that's either a weird edge case or something that requires a human to start annotating things, which won't always be the case. So that brings us to the question of what happens if we're willing to allow the net to have a scratchpad, but don't have any prior knowledge on what to actually write in it. In this case, it seems like the best we can do in terms of determining whether the transformer's uses of the scratchpad is good is to argue that if it ends up getting the right result at the end, then whatever it wrote in the scratchpad must have been right. Whereas if it gets the wrong result at the end, then it must have messed something up somewhere. That's enough information to try to run gradients and to train the net and its scratchpad, but it is somewhat limiting. In this case, it's relative to not having a scratchpad, and it's still possible for you to compute more complicated functions than you could without a scratchpad, but it doesn't really seem to help with learning in a sense, as it won't help with globality. Informally, we believe that if the globality of a task is not constant, then an irregular transformer can't efficiently learn it with a scratchpad unless we know what it's supposed to do with the scratchpad. Intuitively, that's for the same reason as it couldn't learn before that our current transformer model is still some complicated function which we're trying to train by gradient descent. So if none of the derivatives of its behavior with respect to the parameters are correlated with the thing we're trying to learn, it's not going to get anywhere. In the specific cycle test from before, the proof still carries over, so we know it can't learn that one. The more general case is still just a conjecture. So in summary, define the idea of globality degree to measure the difficulty of learning a given task with a transformer. In conjecture, or that for tasks with high globality degree, we can't learn it with a transformer, and an agnostic scratchpad isn't going to help. We then proposed the idea of an inductive scratchpad as a variant where the scratchpad forces this transformer to just perform the same computation in a series of steps to make it generalize from what it was doing in one step to what it was doing in other steps, and cut down on the relevant context length, which does significantly improve length generalization results, also in various tasks. And in general, for these transformer tasks, if we take a transformer without a scratchpad, and constant or logarithmic depth is limited to computing functions that can be computed by TC0, TC1 circuits, whereas allowing it to have a scratchpad boosts its capabilities all the way up to arbitrary computable functions, or polynomial time computable functions if we limit the scratchpad's polynomial length. However, this mostly doesn't help with learning in the sense that we think that we're limited to learning things with low globality unless we know what it's supposed to be doing with the scratchpad and use that to help train it. Thank you. Any questions?
It seems if somebody were applying this, it seems fair to supervise the training of the scratchpad, and the question would move on to how to do that. Right?
Fair in what sense? I mean, if you're trying to learn that parity function, and from before, if you already knew what the correct how to compute the parity, the ith component of the parity, then you wouldn't really need to train a transformer to begin with. You could just do that to be.
Yeah, that's right. Obviously, you can't just list every task and explicitly train it on every task. I guess it would have to be that there are big classes of reasoning tasks, and that there's still some generalization within those classes, right?
Yes, that is a possibility.
Do you have any questions on Zoom?
I have a question. One thing I was curious about, I didn't quite understand how your scratchpads work. But say if I change the transition function in the process, will it be? I presume if it's learning the transition function from trial and error with supervision, then it will at first the accuracy will decline and then it will improve again. Is this how it works, or what will happen if I change the transition function, retaining the same Markov property of the property, etc.?
So from what I understand, I think so if you kind of retrain once with some transition function at the training and then change the transition function at test, I think it would be a kind of a new kind of OOD problem. And now I think it depends how much of a change that the new transition function kind of makes. But I think the main power of this this inductive scratchpad is basically the fact that it kind of forces you to compose things, and it also has this dynamic number of compositions, so you're not limited to the number of that you see during training. But I think in the sense that you should have so for example, you can have different functions, like functions f1 to fn, but I think at least the current format requires you to see it requires that you have seen all of those functions during training, maybe not with the same composition that you're trying at test, but still I think you have to see them. But if you have different functions like f1 to fn, and you can have different new combinations of them at or new patterns of them at testing, and I think that is also something that the inductive scratchpad helps with.
Okay.
If no one has more questions, let's thank our speakers again. Thank you very much.
Thank you for joining us.